Hello everyone, and welcome to 131A, Week 1, Lecture 2. We begin by recalling the material that we have covered in the previous lecture. We have discussed the well-ordering principle of the natural numbers, the principle of induction, a quintessential tool for proving various properties that hold for every natural number n simultaneously, or starting from some given integer. Third, we have demonstrated that the equation x squared minus 2 is equal to 0 has no rational solutions, motivating the introduction of a larger number system R. We have discussed various properties of the ordering and the absolute value on the real numbers. And finally, we have established the triangle inequality and the associated reverse triangle inequality. Today, before moving on to a new topic, we consider one more inequality, namely the one that relates the ordering on the reals and the power operation. We have the following power inequality. For every natural number n and for all real numbers x, y, if we have that 0 is less or equal than x is less than y, then we also have that 0 is less or equal than x to the power n is less than y to the power n. Towards the proof of the power inequality, we first establish the following claim. Suppose that a, b, and c are real numbers if we have that a is less than b and 0 is less than c, then the product a times c is less than b times c. Let's prove this claim first. By the fact relating the ordering on the reals with multiplication discussed in the previous lecture, we have that a times c is less or equal than b times c. So the only difference with the claim we are making now is that the inequality is strict. Okay? So suppose towards contradiction, that a times c is actually equal to b times c. So we're trying to rule out this case and obtain a strict inequality. Yeah? So in this case, we have that also bc is less or equal than ac in particular. And since we have that c is greater than 0, the inverse c to the minus 1 is greater than 0 as well, by the same fact discussed last time. So multiplying both sides of the inequality BC is less or equal than AC by the positive number C inverse, we obtain that B, which is equal to BC C inverse, is less or equal than AC C inverse, which in turn is equal to A. And so we get B is equal to A, which contradicts the assumption that A is strictly less than B. Hence, the claim is established. Next, we proceed to prove the power inequality by induction on n. We let P of n be the assertion that for all xy in R, if we have that 0 is less or equal than x is less than y, then x to the power n is strictly less than y to the power n. The base case P of 1 is obviously true because 0 less or equal than x is less than y implies that 0 is less or equal than x to the power 1, which is just x itself, is less than y to the power 1, which is just y itself. For the inductive step, we show that P of n implies P of n plus 1. So suppose that P of n holds. This means that for every xy in R, if 0 is less or equal than x is less than y, then 0 is less or equal than x to the n is less than y to the n, and we want to use it to deduce the same statement for n plus 1. Towards this, let x, y be arbitrary real numbers, such that 0 is less or equal than x is less than y. Then we have x to the power n plus 1 is just x to the power n times x, which is less or equal than x to the power n times y by the basic properties of multiplication and the order discussed in the fact in the previous lecture. Using that x is less or equal than y and x to the n is non-negative, now we get that this is less than y to the power n times y by the claim that we have just established, and using the inductive assumption that x to the n is less than y to the n and 0 is less than y, and y to the n times y is just y to the power n plus 1. So combining these observations, we conclude that x to the power n plus 1 is strictly less than y to the power n plus 1. Finally, since we have that 0 is less or equal than x to the power n and 0 is less or equal than x, we conclude that 0 is less or equal than x to the power n plus 1 by the same fact that multiplication preserves the ordering on the real numbers. Hence, our power inequality is proved. We move on to the new topic, the real numbers and the completeness axiom. Let's begin with the definition. Let S be a non-empty subset of the set of real numbers. 1. The largest element of S assuming that there is one is called the maximum of S and is usually denoted by max S. Similarly, the least element of S, if there is one, is called the minimum of S denoted by min S. Let's consider a couple of examples. 1. Every finite non-empty subset S of the reals has both a maximum and a minimum. So if we present this on the real line, we have 0 and an arbitrary finite set of elements S, then the minimum corresponds to the leftmost element and the maximum corresponds to the rightmost element of this finite set. Another example, let A less than b be two arbitrary real numbers, then we can consider the closed interval denoted as the closed interval between a and b, which by definition consists of all real numbers x, such that a is less or equal than x is less or equal than b, so the endpoints a and b are included, has a minimum which is just the left endpoint a, and a maximum which is just the right endpoint b. In contrast, the open interval AB, which by definition consists of all the real numbers x, which are strictly in between a and b, has neither a maximum nor a minimum. So if we depict this on the real line, the closed interval AB consists of all points in between a and b, including the point A and the point B themselves, while the open interval AB consists of all the points that are strictly in between A and B, excluding the endpoints A and B. And so there is no maximal element, because no matter what element we take, if it is in the open interval AB, it has to be below B, but we can always choose an element which is still below B, but to the right of the element that we just picked. So we have an element in that interval which is above this prescribed point, hence there is no maximum. And the argument for the minimum is similar. Third example, we can consider Z and Q, which are both subsets of R, the set of reals. Neither of the sets has a minimum or a maximum. The reason for this is that if we depict either of the sets, so for example, the set Z, which consists of 0, 1, minus 1, 2, minus 2, etc. Now if we take an arbitrary integer a in Z, we can always consider a plus 1, which is also going to be an integer, and demonstrates that a is not the maximal element of Z. The argument for the non-existence of a minimum is symmetric. Apart from the minimal and the maximal elements of a set, we can also talk about the upper bound and the lower bound. Towards this, we make the following definition. Let S be a subset of the reals, non-empty. We call a real M an upper bound for S if M is greater or equal than S for all elements little s in the set capital S. If such an upper bound exists, we say that S is bounded from above. Similarly, we call a real number little m a lower bound for S if we have that m is less or equal than S for all numbers little s in the set capital S. If such a lower bound exists, we say that S is bounded from below. finally, we say that S is bounded if it is bounded from above and from below. Let's look at some examples. The maximum of a set, assuming it exists, is an upper bound. Similarly, the minimum of a set, if it exists, is a lower bound. Let A less than B be arbitrary real numbers. Then A is a lower bound for both the closed interval AB and the open interval AB. Indeed, let's draw it on the real line. So we have A and B, and we can consider both the closed interval AB and the open interval between A and B. Now it's clear that the number B is above every element of either of these two intervals, and A is below in the sense of being less or equal than any number in either of these two intervals. Of course, this example, it's easy to see that the lower bound and the upper bound are not unique. So in particular, taking any real number, C above B, we see that C is also an upper bound for either of these two intervals by definition of the upper bound. And similarly, taking some real number D below A, we still get that this is a lower bound for both of these intervals. In fact, for each of these intervals, A is the largest lower bound and B is the smallest upper bound. 3. Neither of the sets Z or Q are bounded from below or from above. As the example with the intervals illustrates, not all upper bounds are equal. So some of them are more optimal in the sense that they are below every other upper bound while still being an upper bound for the given set. And similarly for the lower bounds. So now we make a definition which makes this precise. Definition. Let S be a subset of R, non-empty. 1. If the set S is bounded from above and it has a least upper bound as 0, then we will refer to this least upper bound as 0 as the supremum of the set S. Symbolically, this is written as S0 is equal to the supremum of the set S. Similarly, if the set S is bounded from below and has a greatest lower bound S1, then S1 is called the infimum of the set S, and symbolically this is written S1 is equal to inf S. Let's make some remarks concerning these definitions. 1. Every set S, a subset of the reals, which is non-empty, can have at most one supremum and at most one infimum. This is just a consequence of the fact that a given set can have at most one maximal element and at most one minimal element, and the supremum is the minimal element of the set of the upper bounds of our set, and the infimum is the greatest element or the maximal element of the set of the lower bounds of our set. 2. If the set S has a maximum, then the maximum of S is equal to the supremum of S. 3. The following are equivalent. A. S0 is the supremum of the set S. B. We have that S0 is greater or equal than S for all elements little s in the set capital S. And if S1 is greater or equal than S for all elements S in S, then S1 is greater or equal than S0. So this is just a rephrasement of the property of being the least upper bound. And C, S0 is greater or equal than S for all S in S. And we have 2 prime. If S1 is less than S0, strictly less, then S1 is less than S for some element S of the set capital S. Each of B and C is just a straightforward reformulation of the definition of the supremum, but in practice sometimes it's easier to check one of these explicit conditions. Example. Given a pair of real numbers, a less than b, we have that the supremum of the closed interval ab is equal to the supremum of the open interval ab is equal to b, and similarly the infimum of the closed interval ab is equal to the infimum of the open interval ab is equal to a. Let's consider another example. Let's look at the set A, which consists of all numbers of the form 1 over n squared, where n is a natural number, and n is greater or equal than 3. Then this set A is bounded from above and from below. It has a maximum, which is equal to 1/9, but no minimum. Indeed, since we can increase n arbitrarily, we see that the element 1 over n squared gets smaller and smaller. So there is no smallest element in this set. However, there is an infimum, and in fact we have that the infimum of A is equal to 0. Indeed, 0 is a lower bound. Every element of the form 1 over n squared is positive when n is a natural number. And this 0 is the greatest lower bound because we can always choose n sufficiently large so that the number 1 over n squared gets arbitrarily close to 0. And finally, the supremum of A is also 1/9, just at the maximal element. Because by the previous remark, we know that if there is a maximal element, then it's equal to the supremum of the set. However, note that in general, neither the infimum nor the supremum of a set have to be in the set themselves. In this example, 0 is not an element of A, however, it is the infimum of A. With the notions of the supremum and the infimum at hand, we are ready to define the characteristic property of the real numbers, the so-called completeness axiom. It says that every non-empty subset of the real numbers which is bounded from above has a least upper bound. In other words, given a set S, a subset of R, which is non-empty, if S has at least one upper bound, then the supremum of the set S exists. This axiom gives us a precise way to express the intuitive impression that there are no gaps on the real line. Before looking into this further, first let's observe that the completeness axiom fails for the rational numbers. Let's consider the set A consisting of all the rational numbers R, such that 0 is less or equal than R and R squared is less or equal than 2. Equivalently, the set can be described as the set of all rational numbers R, such that 0 is less or equal than R is less or equal than the square root of 2. Note that the set A is bounded from above So for example, the rational number 3/2 is an upper bound. Now, the supremum of the set A is equal to the square root of 2. Remember, however, that in the last lecture we have proved that square root of 2 is not a rational number. So it's a real number, but not a rational number. Hence, the set A, which is a subset of the rational numbers, does not have a supremum or the least upper bound within the set of rational numbers itself. So this shows that the completeness axiom distinguishes the real numbers where it holds from the set of rational numbers where it doesn't hold, as witnessed, for example, by this set A. Now, the completeness axiom is formulated with respect to the upper bounds. There's nothing special about it, and we can equivalently obtain a completeness axiom with respect to the lower bounds. So let's make it precise. Corollary. Every non-empty subset S of R that is bounded from below has a greatest lower bound inf S. Proof. Given a set of real numbers S, we define the set minus S to consist of all real numbers of the form minus S where little s is an element of the set capital S. If we draw it on the real line, this corresponds to the reflection around 0. So if we're given a set S, for example, of this form, then the set minus S is going to correspond to its reflection around the 0. So we have a set of the form like this. Okay, so this is minus S. By assumption, S is bounded from below. This means that there exists some real number m in R such that m is less or equal than S for all elements of the set capital S. Multiplying both sides by -1, this implies that minus m is greater or equal than minus S for all S in S. In other words, we have that minus m is greater or equal than u for all u in the set minus S, by the definition of the set minus S. That is, minus S is bounded from above. By minus m. By the completeness axiom, for the set minus S, we have that the supremum of the set minus S exists. Let's look at the picture again. So we started with m, which gave us a lower bound for S. And we have observed that minus m provides an upper bound for the set minus S. The completeness axiom for the set minus S provides us with an element corresponding to the supremum of the set minus S. Again, looking at the symmetry of this picture with respect to 0, it's natural to expect that the infimum of the set S should correspond to minus the supremum of the set minus S. Indeed, this is what we're going to prove in a moment. Let S0 be the supremum of the set minus S. We need to show that minus S0 is less or equal than S for all elements S in S, and that if T is less or equal than S for all S in S, then T is less or equal than minus S0. If these two conditions hold, then minus S0 is indeed the infimum of the set S. Because the first claim shows that minus S0 is a lower bound for the set S, while the second condition shows that minus S0 is the greatest lower bound. That is, that minus S0 is the infimum of S. Now, by the choice of S0, we have that S0 is greater or equal than every element of the set minus S. Hence, it is greater or equal than minus S for all S in S. And this implies the desired condition, multiplying both sides of the inequality by -1. For the second part, assume that T is less or equal than S for all S in S. This is equivalent to minus T greater or equal than minus S for all S in S, multiplying both sides of the inequality by -1, which is equivalent to minus T greater or equal than S prime for all S prime in the set minus S. by the definition of the set minus S. Hence, since S0 is the supremum of the set minus S, this implies that minus t is greater or equal than S0. And finally, this is equivalent to t less or equal than minus S0. Finally, we are ready to answer the motivating question from the first lecture: what are the real numbers? From the point of view of this course, the answer is going to be that R is a number system which contains Q, the rational numbers, and satisfying the completeness axiom. Of course, the term number system used here is somewhat imprecise. Technically, the real numbers is a so-called ordered field. Essentially, it means that the operations plus, times, and the linear order satisfy a certain list of axioms, which you're already familiar with, which correspond to the basic properties of these relations given by the fact in the first lecture. For the rest of the course, we will only need to know the basic properties of plus, times, and less or equal for the real numbers, as well as the completeness axiom. Everything else will be deduced from it. We begin by establishing some of the important consequences of the completeness axiom. The first one is the Archimedean property. The following properties of the real numbers hold. 1. For every positive real number A, there is a natural number n such that n is greater than A. The second condition: for every pair of positive real numbers AB, there is a natural number n such that n times A is greater than B. And the third condition: for every positive real number epsilon, there is a natural number n such that 1 over n is less than epsilon. Of course, each of these properties might seem obvious from the common experience with real and natural numbers. However, it's a fundamental property, and to rigorously establish it, we have to use the completeness axiom. Let's begin with a proof. 1. Assume towards contradiction that there is a positive real number A such that A is greater or equal than n for every natural number n in n. In particular, this means that A is an upper bound for the set n, a subset of R. Now, by the completeness axiom, we can take some b, a real number, such that b is the supremum of the set of natural numbers, as b is the least upper bound of the set n. The number b minus 1/2 is not an upper bound for n, because it is strictly less than b. In particular, this means that there exists some natural number n such that n is strictly greater than b minus 1/2. Adding 1 to both sides of this inequality, we obtain that n plus 1 is greater than b minus 1/2 plus 1, which is greater than b. This means that n plus 1 is a natural number, so an element of the set n, which is greater than b. But this contradicts the choice of b, which was chosen to be an upper bound for the set n, right? So hence our assumption was incorrect, and it means that for each a real number, there exists some n greater or equal than a. Now we know that 1 is true, and we use it to prove 2. Suppose that we are given real numbers a, b greater than 0, so both are positive. In particular, this implies that b over a is greater than 0. Using 1, there exists a natural number n such that n is greater than b over a. Multiplying both sides of the inequality by a, we conclude that n times a is greater than b. So this gives 2. Finally, to prove 3, we suppose that epsilon is a positive real number, then we know that 1 over epsilon is also a positive real number. By 1, there exists a natural number n such that n is greater than 1 over epsilon, and multiplying both sides by the positive number epsilon over n, this yields that epsilon is greater than 1 over n. The Archimedean property has many useful corollaries. For example, it tells us how to find integers in large gaps between two real numbers. So more precisely, suppose that we have a less than b real numbers and b minus a is greater than 1. So the gap between b and a is greater than 1. Then there is an integer m such that a is less than m is less than b. So m is strictly between a and b. Let's prove this corollary. By the Archimedean property, there exists a natural number k greater than the maximum of the absolute value of a and the absolute value of b. In particular, we have that minus k is less than a is less than b is less than k. we consider the set K consisting of all integers j such that minus k is less than j is less or equal than k. And we also consider the set K prime, which consists of all those j and k such that a is less than j. Note that both of these sets are finite and non-empty. As k is an element of the set K prime, which in turn is a subset of k, we define M to be the minimum of the set of all j in k such that a is strictly less than j. Then we have that minus k is less than a is less than m, and as m is greater than minus k, we get that m minus 1 is an element of the set capital K. So m minus 1 is less or equal than a is less than a plus 1 is less than b. We have this by the definition of m and the assumption that b minus a is greater than 1. Now adding 1 yields that m is strictly less than b, and so a is less than m is less than b, as wanted. Finally, we use the Archimedean property to establish the density of Q in R. What does it mean? Suppose that we're given an arbitrary pair of real numbers, a less than b. Then, no matter how small the gap between a and b is, we can always find a rational number r such that this rational number r is strictly between a and b. Let a less than b real numbers be given. We need to find a pair of integers mn such that n is positive, and we have that a is less than m over n is less than b, because then taking r to be the rational number m over n satisfies the desired inequality. Now, multiplying by n, this is equivalent to saying that an is less than m is less than bn. This means we need to find an integer m in the corresponding interval an, bn. We would like to apply the previous corollary. So for this we need to arrange that the interval between an and bn is sufficiently large. By the Archimedean property, we know that there exists a natural number n greater than 0 such that n times b minus a is greater than 1. This is given by the second item of the Archimedean property. Equivalently, we have that n times b minus n times a is greater than 1. But now, since the gap between the real number n times b and the real number n times a is greater than 1, the previous corollary tells us that there is some integer m strictly between them. And in view of the desired inequality, we are able to conclude. This finishes the discussion of the basic properties of the rational numbers, the real numbers, and the connection between them. Next time we will discuss the existence of nth roots and real powers. Thank you for your attention.